post a link for you to apply for the SIG test. Notice SIG test. You can write a SIG test where you are sick. That means you must submit the doctor's note. Things such as I couldn't come to campus, not good enough. That's not the reason. You're supposed to be here. This is a residential university. You're supposed to attend lectures, supposed to be on campus. Alright, so that's it. Okay, good. So that's what I wanted to mention with regards to the logistics of the test. So let's start. Remember, what is in scope for the test is chapters 4, 5, 6, and 7. And expect to all any work that we cover during that time. Also, all the pracs up to last week is included in scope for the semester. Let's have a look at what is important for chapter 4. So with chapter 4, you can remember it was all about threads. Now, one of the first things to remember, or one thing that you should know from a structure point of view in the test itself, this question, or the questions based on chapter 4, is a total of 19 marks, 19. So, because there are 4 questions from the theory part, I have to kind of weigh it evenly. So, 3 of the chapters 4, 5, and 6 are 19 marks, and chapter 7 will be 18 marks. And the rest will be the practical stuff that you guys have. Okay, so with the 19 marks, what is important with regards to threads? Threads, not threads. Okay, first thing to remember is that in threads, there's a difference between a thread and a process. If we describe a process, each process has a memory address that it runs in, the start address and the end address is where it physically can get its code, the data, and all of these things, all of these actions. Another thing that defines a process is things such as the number of open files, the list of open files that it has, the type of resources that's currently associated with this specific process. So there's a number of things that each process has unique. Also, the code that we find in the process, you can on a process level, together with data, together with whatever file. But there are things that we associate per thread that we only find in each thread. And that is, firstly, the set of registers. Each thread has its own set of registers associated while we're running that thread. Another thing that defines per thread is things such as the stack. So not only do each thread has its own registers, it also has its own stack that you basically have. So make sure that you know what is unique to a thread, what is shared between threads, what is on the process level, what is and so forth. So this is an important aspect that you need to understand. And then another thing which is important is, why do we write multi-threaded applications? Why do we want to have this? So a number of benefits are, definitely it gives us responsiveness. Now what does that mean? It means that we can have things happening in our process while other things are blocking. So we basically get continuous execution when certain other things are blocked. Another thing is that we get what they call resource sharing is very simple. I mean, we've already seen here that registers share the same code. Share the same data. So typically things like global variables, very easily to share those things between your threads. Where if you do that in between processes, it's a lot more complicated. Remember the previous chapter we had everything about message passing and shared memory and all of that, which was a lot more complicated. Another thing is what we get is economy. It is cheaper to spin up a thread than it is to spin up a whole process. Because with the whole process, you have to assign the number of memory for it, you have to keep track of what resources is running, and all of these things. Where if you just with a thread, the only thing you need to a thread is the registers in the stack kind of thing. So it's a lot less overhead to just spin up a thread, run that thread, and then interact with the other threads rather than another process. And then obviously it gives us scalability. If we run a multi-threaded application on a uniprocessor system, then it doesn't really scale more than another, well, much more than a multi-processors environment. Because with multi-threads, you can easily, when a process gets execution time, you can have multiple threads in that process running concurrently on other, or in parallel rather, on other cores. And it's a lot easier also to switch between threads than you have to do a context switch between processes. I think that was a possibility. Thread switching is lower overhead than context switching. So this is important to remember this. You have to understand what's the difference between concurrency versus parallelism. Concurrency is where we describe the principle is where we can run an actual multiple threads concurrently, but what it actually means is that each thread gets a bit of a time slice on the process. Where with parallelism, if we use that term in this textbook, then we say that we can run multiple threads at exactly the same time. How is that possible? Well, because we've got potentially different CPU cores or multiple CPUs in the system. So those are the differences between what is meant by concurrency and parallelism. And then we talked a little bit about some of the models in which we can implement threads. There are in general 3 different models that can be adopted by operating system developers when they implement threads in their systems. The first one is what they call the many-to-one, then there's the one-to-one, and the many-to-many. Basically, just review each of these. Many-to-one basically means that you can have multiple user-level threads running in your user space, but they all map to one thread running in kernel run. So the kernel scheduler, for instance, do not know about these multiple user-level threads, but the user-level threads, they can be easily scheduled during the runtime that they're in. Then you get the one-to-one model, and there we have a direct association between a user-level thread and a kernel-level thread. And then when we schedule our kernel-level threads, they have a direct effect on the user-level thread as well, because it basically allows each one to run at the same time. Your normal modern operating systems, such as Windows, Linux, Solaris, Higher, and so forth, they use this type of model. Just remember that. And then the last one is this what they call many-to-many model. Now, what is interesting with the many-to-many model is that in certain runtime environments, this model is actually applicable, where we have a certain number of user-level threads that gets mapped to a different number of threads on the kernel side. And what typically happens in between here is that we've got a runtime environment that manages that mapping and it ensures that it runs. A good example here is typically if you run multiple Java processes on your computer, but they all run inside the same Java runtime, then typically that Java runtime machine will handle the user-level threads, which can be multiple, and that Java runtime machine can then map it to a certain number of kernel threads. So those are all possible. Another thing that kind of fits in here is the same principle of thread pools. It also fits kind of with this type of model that we have. But anyway, that's not that important for that section. Okay, next is when we look at threads, we also talked about different ways in which we can implement threads. This is what they call implicit threading. With implicit threading, it basically means that we wanted to make it easy for developers to use multi-threaded systems, and I specifically demonstrated OpenMP to you guys. I showed you guys how we can use it with C++. Very, very simple create a system that can run a number of threads in parallel. In fact, when you've got a section that describes parallel, it basically will spin up a number of threads and it will run that code section in whatever number of cores you have inside your, or let's put it, virtual processors that you have inside your computer. And I demonstrated in my computer where you've got such a parallel section that it spinned up, I think, 8 of these threads on my computer because I had 4 cores, each one had a hyper-threading component implemented on it, which basically is 8 virtual processors on my computer. So just be aware of the MP and everything that goes on with that. That is what is important for chapter 4. Stop this now. Right, let's have a look at chapter 5. So chapter 5, this maps the question 2 in the test. You can expect also this question to be about 19 marks and different sections in it. So chapter 5 describes how we synchronize processes or threads inside the system. And the reason why we want synchronization is that you want, typically if you've got multiple processes or multiple threads running on a system, they sometimes work together, and we use a principle of the consumer and the producer aspect that describes certain types of process where one thing produces and another thing consumes, and you get this in different threads, and you get this in processes as well, and how you should synchronize these workings between these multiple processes. And we also discussed in here some of the problems that we can get when we have these multiple threads or multiple processes where they share certain memory or share certain resources between each other. So the first thing that you need to know is when we have multiple processes running, sometimes they do get into this principle of a racing condition, and then a racing condition basically appears in a special section of our code that we call a critical section. So what is a critical section? Critical section is where we have some code that potentially changes some common variables, like can be other resources such as updating tables, writing files, etc. And we typically call it a critical section because we want only one process or thread to be in their critical section at a time. So while one thread is busy executing that code, we don't want any other copy or any other process to also access that critical section that accesses the same variables. That is typically what we call a critical section. And a critical section consists, and when we look at code, we basically can describe the different sections in our code so that we can evaluate the critical section. And normally, when we look at this problem, we identify what we call the entry section of our code. So before something gets into its critical section, there's normally an entry section that helps us make a decision of, okay, who can get access to this critical section. Then we've got the physical critical section component, which is this section here in the middle. And then once your process has finished the critical section, then it goes to an exit section. And the exit section is also normally important because that can sometimes wake up other processes that might be going into its critical section, that might be stuck in its entry section, and so on. So the exit section and the entry section kind of works together. And then obviously we've got our remainder section. That is whatever is left in our code. So make sure that you understand what these different sections are, make sure that you know what is a critical section, what defines a critical section, and so on. To handle this entry into this critical section, we described a number of solutions, and some of these solutions requires that we have to make changes in the hardware of our computer. So if we look at the hardware of our computer, I mean, Peterson's solution is a nice solution that just describes from the software perspective how things work. But for Peterson's solution to be properly implemented, or any of the solutions that comes after this, there must be some kind of support built into the hardware to make it possible. Now, there are two major ways in which this is implemented. The first implementation is where we disable the interrupts in the system. And the reason why this is important, if you think about, now this only really works on a uniprocessor system, is remember when we get this, when a piece of code runs and it then gets time sliced, and it's because of the timer that runs out. Remember, we've got this quantum timer that starts counting down, and when it gets to 0, it raises a timer interrupt, and then the scheduler will start. But if it cannot raise a timer interrupt, meaning we've disabled the interrupt, then it cannot be interrupted. So that's one solution, but it can only work if you have a uniprocessor system, meaning one processor. What is interesting is that this disabling of interrupts is kind of how even the atomic instructions kind of work as well. But they've got a little bit more fancy later on when they started creating what they call atomic instructions. And that is the second thing that gets built into our processors. So atomic instruction is an assembly instruction so that when it runs, even though it takes multiple clock cycles to run, while it's doing its work, it cannot be interrupted. The processor, through its hardware, through its hardware architecture, will ensure that once an atomic instruction runs, no other, or that atomic instruction will complete and it will not be interrupted. So that's that's the second great thing of how we modify the hardware to support all the other solutions that we have for our process synchronization. So that's the hardware aspect. Then we went into a bunch of solutions from, okay, so here's just some of the hardware instructions, the atomic instruction principles that we get, blah, blah. And then some of the principles that was built on top of it, started talking about mutex locks. Now mutex locks, remember, was just a busy wait solution. And then it went and we discussed semaphores. And we said that a mutex lock is really just a thing that's a flag that says you're either engaged or not engaged. And I like to use the whole bathroom door as a good analogy of what a mutex lock is. So while someone is inside the bathroom stall and says I'm engaged, then no one else can get in there. So the flag is raised, or you can't get in here, and then you have to wait for the flag to drop, and then the next guy can go. That's effectively what a mutex lock is. The semaphore, however, is a little bit different. Because you get two versions, well, you get a number of types of semaphores. We talked about binary semaphores, you get counting semaphores. And counting semaphores, we said, is ideal if you want to give access to a certain number of resources. So if you've got, let's say, 5 printers, and you want to allow these 5 printers to be fully utilized, you can create a counting semaphore, and as a process goes into its critical region, to start printing, you can assign a specific printer to each process by using the counting semaphore to handle that. The first and another type of semaphore we said here was what we called the busy wait semaphore, which was the first one that was described here, which was the wait and the signal one. And then we described another type of semaphore, which was the non-busy wait one. Yeah, this one. So with no busy waiting. So what does busy wait again mean? So let's just quickly recap what that actually means so that you can understand here. Busy waiting basically means that in the code, the CPU gets to a point, it does a test, and then it keeps on repeating that test over and over and over and over again. It actively runs code to test whether the flag is up or down or not. That's called busy waiting. This solution, the no busy waiting solution, actually says that instead of our processes staying on the ready queue, meaning consistently going from ready to running, what we do is we move that process to the waiting queue. And as soon as you're on the waiting queue, you're basically asleep. And that's what this semaphore allows us to do. So this semaphore has the following structure. So to take note of the structure, this is a typical C++ structure that describes this type of semaphore. The first thing is, again, just like all the other semaphores, it may have a value. And again, if the value is potentially negative or something like that, or a 0, then the process means you have to go to sleep. But also associated with this semaphore is a list of processes. And whenever a process sees that it cannot enter its critical region, then it will voluntarily say, I'm going to go from the ready queue to the waiting queue, and then it adds itself to that list. And then when a process that was in its critical region now exits its critical region, remember we have this whole exit code that we talked about. Here's the last one. Release the log or something like that. So, yeah, but if you can remember, that's the last portion of the code, or the second last portion. When we exit the code, we will do what they call a wake up, and then the wake up instruction will select one of these processes that's on the list. And it will then send a signal to that process, and that process will then be moved from the waiting queue into the ready queue so that it can start running at that point. So that's one great thing. Well, that's what semaphores allow us to do. Instead of wasting CPU time spinning the whole time, busy waiting, it actually lets them sleep. And the structure that allows us to define such a semaphore is this C++ structure. So that's what semaphores. And then this chapter ends with this principle of what we call deadlock. Now there's a difference between a deadlock and a critical region. Deadlocks do occur because of some critical resources potentially, but they don't have to. We can say a system is in a deadlock when one process is waiting on another process and each of them are waiting for resources that the other one is holding on to. There's always more than one resource, and both of them are holding on to resources that the other process is using. And hopefully you can remember in the class we had two students here. The one had a pen, the other one had a paper, and the task was given to both these two students to say, go write something. But because the one student was holding the pen and the other one was holding the paper, they could not complete their task. That was deadlock, and we then went into describing how we can graph these deadlocks. Now, so the same principle still is true that when we graph a system to detect whether we're in a deadlock or not, we describe a process using circles, we describe resources using squares, but the textbook talks about little instances inside a square that describes the number of those resources. You don't have to worry about it. Okay, so the only type of problem that you will get for this is where there's one such type of resource. So one resource is always just one square, forget about the stuff that's in there. Then we have the vectors, or the arrows. When an arrow points away from a process, think about, here's the process I'm pointing away, is that I want, meaning I'm requesting something, and if you're holding on to, look at me, I'm grabbing stuff, I'm pulling it towards me, that is when you're holding something. So an arrow points towards the process when it's holding a resource, when it's requesting a resource, points away, and the deadlock occurs when we've got a circular situation that occurs, when you follow the arrows and you will go into an infinite basic circle and will never stop. If the arrows, you get to a point where two arrows point towards each other or away from each other, then you know that is not a deadlock situation. So you need to know how to draw these resource allocation graphs and interpret whether the system is in a deadlock or not. There is a video on the lecture notes, or sorry, on the notices that you can have a look where this is demonstrated. Just a reminder. Okay, that is this chapter. That's chapter 5. Let's have a look at chapter 6. Yes, chapter 6 is resource scheduling. So a lot of this chapter, you should remember your extra documentation that I've uploaded on here that kind of summarizes a number of these algorithms and how you can interpret these algorithms with regards to how much CPU time each process will get. So, again, this is question 3 in the test, and it's also 19 marks. That's CPU scheduling. First thing here, remember the short-term scheduler will decide which process to run next, and the times when the scheduling decisions are made. There are four instances of when these types of scheduling decisions are made. The first is when it switches from a running to a waiting state. So effectively we were running, and now because we did an IO request, we go into a waiting state. So immediately our time quanta hasn't expired. We now say, I want to print something, I want to save a file. Anything where you do an IO request at that point, where we potentially have to block, and then we go to our waiting queue, that's when the next decision or the next process gets selected. Another one is where we then move from a running to a ready state. Now why will that happen again? That's typically when our quanta has expired. Meaning the little counter in our timer expired, it raises an interrupt, and then it selects, okay, you're now going from running to ready. And then also, when it switches from waiting to ready. Now waiting to ready, process moves from waiting to ready, remember? So they've done the whole IO requesting, and now the buffer contains the data that we've requested has now been loaded into the memory of your computer. An interrupt basically tells the computer, hey, the new data is there, you can now get this, run this process again, and that will then take that process and it will move from waiting into a ready state. It won't go directly into running, it will first go into a ready state, and then again, you may get a scheduling decision to be made. And obviously the last one was, we were running. So we were running there, but now our process is finished. So we need to terminate. There must be, because it's not running anymore, we have to select a new one. And what is of interest here is that instance number 1 and 4, this is what we call a non-preemptive scheduling. Now, non-preemptive scheduling means it's the process that says, I'm not running anymore. So if you can actually, that kind of makes sense, because if you think about it, in the first instance, the process is scheduling something from the hardware. It goes and says, I want to go save a file, or I want to go read the data. So the process goes and says, I'm now done, and it says voluntarily relinquishes its CPU time. And also the last instance as well. So there the process has finished, so it again voluntarily says, I'm finished now, I'm done, someone else can now run on this process. That's called non-preemptive scheduling. All the others are what we call preemptive scheduling, meaning while something is running, we can stop the thing that's running and select another process to run. The first one was obviously because of the counter, and the second was when a new interrupt occurred because of IO that became available or finished the IO request at that stage. Right, so that's when the CPU scheduler gets activated. Now when we look at CPU scheduling algorithms, and as a computer scientist, you want to develop your own algorithm, or even as a developer, you want to develop your own algorithm. there's a number of criteria that you have to take into consideration. And this is the 5 criteria that is of importance. The first is our CPU utilization. That is, any kind of algorithm we develop, we want to make sure that our CPU is kept as busy as possible. We don't want the CPU to be idle, otherwise we're just wasting the CPU time. Throughput, we want to make sure that the number of processes that complete that execution is as much as possible in a specific time unit. We also want a certain turnaround time, that is the amount of time to execute a particular process. We want to have it fast, so when a process becomes available, we don't want to wait forever for that process to get some CPU time. So yeah, that's for it to execute actually. Waiting time is how long it will wait before it can actually execute, and response time is the amount of time it takes from when the request was submitted until the first response is produced. Not so much the output, but when it actually starts executing something in the system. So those are the 5 criteria, and you can actually see here, typically when we look at an algorithm, this is kind of what we want. So we want maximum CPU utilization, maximum throughput, minimum turnaround time, minimum waiting time, and minimum response time. Okay, the next so one of the scheduling algorithms that we talked about was the whole priority scheduling algorithm. And in priority scheduling algorithms, because we have certain processes that has a higher priority than other processes, we may get a problem if the algorithm is written badly, that we get what they call starvation. Now, what is starvation? That is when we've got a low priority process that basically never gets executed. So I basically used an example here in the class where we said you've got a little stand maybe here, and a bunch of students wants to maybe buy food from you. And the students are maybe a low priority, and the lecturers are maybe high priority. The lecturers can jump the queue. So and then eventually the students can never buy food, and then they will die. Okay, so that was the idea. That's called starvation. Now, a solution towards starvation is what they call aging. So basically, what we do is we look at the time that our low priority process is in the queue, and as they grow older, we basically make them more important. And there's a number of these algorithms that we have used in our extra lecture notes that specifically looks at that scenario where we say that if you have 2 approaches there, either you make your high priority processes lower, or you take your low priority processes and you make them higher. The examples in the extra lecture notes is really the first one, where you take a high priority process, and as time goes by, you basically let them go to a lower priority after a certain either one quanta or sorry, after a certain number of quanta has expired. Okay, so that is also important to understand. I am not going to now revise the extra lecture notes again with you, but please make sure that you understand what round robin means. Round robin, remember, if you've got multiple processes, that's typically in a preemptive system. Multiple processes, each gets a certain quanta, and then round robin basically just means it takes whatever in front of the queue, gives it processing time, and puts it at the back of the queue again. So always think in terms of queues with these things. That's important. Think of a queue, and basically, when you're finished with the front, and you're not finished executing, you have to go sit at the back of the queue again. That was the principle of round robin. We talked about multiple levels of priority. Typically, a process with a higher level priority, and remember, when we define high level priorities, it's typically with a low number. Weird, eh? So just remember that. So, like a priority 1 is actually a very high priority, and a priority 5 is a low priority. Just remember that weird inverse thing that we talked about. And then if you've got multiple processes on the same priority, we will tell you how to handle it. So first come, first serve, round robin, whichever way, and if it's preempted, it's typically something like a round robin situation. And then we also, into the mixture, said that we can, it's possible to have certain algorithms where we've got a decrease in priority. And the example there started where we had, let's say, a priority 1 process that ran for a certain pointer. And then immediately after it ran, you increase its priority, meaning you add 1 to its priority, then you decrease the priority. So the next time it will be priority 2. But remember, when you go from one priority to the lower priority, you always go sit in the back of the queue. Okay? You don't jump the queue, you go sit in the back of that specific queue. So the best way to visualize it is visualize that each priority has its own queue, and depending on where you are in that queue. So remember, those extra scheduling content is important. Then the last thing that we talked about is when we look at multiple processor systems, it is important for us to understand that we schedule certain processes and we try to keep certain processes local to physical CPUs because of a potential architectural principle called NUMA. What is NUMA? NUMA stands for non-uniform memory access. And NUMA basically means the following, that you get multiple processors in the system. So here we've got a processor, here we've got another processor, or a core, or whatever, and you have different memory sets, physical memory in the computer. Some of these memory are closer to other CPUs than in other areas, in other environments. And what the closeness basically means is that some of this memory is accessible through fast access. So in this diagram, you will see that this memory here can easily be accessed very quickly rather than the memory that's on the other side of the motherboard. So that's NUMA architectures, and the reason why this is important for us to understand is because when we run typically processes that's multi-threaded, we want those threads that cooperate typically, or processes that operate, to be in the same CPU or CPU set. So that they can share things together and so forth, so they can get access to the same memory. So if they exchange data, you don't have to do it over slow access. And that is the principle of NUMA that is important. And that is chapter 6. Let's have a look at chapter 7. And chapter 7 starts with main. This is where we start with memory, and we'll end it this morning, or this afternoon rather. So in main memory, one of the first mechanisms we discussed was this idea of switching off processes. So when we switch processes, or actually we call them swapping. We take a full process, we swap it into memory, and then we run it, and then when we're done, we can swap it away again. But the problem with the swapping is we needed this contiguous memory block that we wanted to swap our process into. Finding such a block, getting a hole, that's what it's called. A hole is what we declare as a contiguous piece of memory addresses that we can use for our swapping our process into, we use different algorithms for this. And we had the first fit, the best fit, and the worst fit. And I demonstrated how we typically can do this using Excel. And there's a video on Eve again, a link to the video on Eve that you can watch, in which it describes a problem where you may have a number of holes, A, B, C, D, E, F, G, H, whatever, and then you've got a process, a number of processes that you want to potentially swap in. And then you can have to apply either the first fit, the best fit, or the worst fit scenario with this. And when I discussed this with the student, and I mentioned this in the video as well, the best way to think about this is to think about buying clothes. You can never fit into anything that's too small for you, but you can always fit into something that's bigger than you. So if you've got a certain size, let's say my quantity size is 13, then I can fit in with clothes that's 13, 14, 15. Anything that's bigger than me, I can fit into. That's one way that you can think about it. So best or first fit basically means you go look at your clothes that's hanging on the rack, and you start from the left to the right, and you select the first piece of clothing that you will fit into. Once you've used it, that clothing then shrinks to whatever size is left that you haven't used up. That's important to remember. Those things do change. And then when you get another request, and I now need to fit another size, again you start from the front, and then you select the next one. The first one, sorry, that's not the next one. The first one, always from the start. You select, and that's what the first fit means. The advantage of first fit is the seek time to find such a hole is on average half of the linked list size, because half of the time you potentially will find something else. They're not, so it's not a bad solution with that, but it can obviously create this fragmentation problem. Well, any of these creates fragmentation problems. Then the best fit solution looks at all the clothes. So you basically go to your closet, you take out all the clothes that will fit you, anything that's bigger than you put them on your bed somewhere, and you find the clothing that's the one that fits you the best, the one that means you're not going to have much left afterwards. Remember to update, once you've selected that clothing then shrinks to the smaller size of whatever value is left, and you put it back in your closet. And then the worst fit is you look at the one that's too big, and you try to fit in that one so that you've got the biggest hole left potentially afterwards. Those are the three algorithms. Again, look at the video if you're not sure of how this is accomplished. The next thing is we talked about paging. So the whole swapping, we said the bad thing about swapping processes in and out is that processes are fairly big, and writing that process to the back-end store in the hard disk takes a significant amount of time, and then reading that new process into my memory is also quite slow because they're so big. So instead of having these big bulky things, we created, or the very intelligent people created this principle of paging, where they said, let's break up our process into smaller chunks. And we call each of those chunks a page. And I physically had a number of pieces of paper here. So just remember, one piece of paper is what we call one page. It's also called a page frame. It looks like a frame because it's a nice rectangle. But on this page, potential, or in this page, there's a number of memory addresses there. And then we said that when we look at any request and we look at the logical address, that means we have to understand that there's logical addresses and physical addresses. We translate from logical to physical. The logical address we typically break up into two sections. The leftmost section describes the page number, and the rightmost side is what we call the page offset. Where inside that page we will find the information that we want in the actual memory address. The page numbers and the page offset is typically some kind of number, value. And that value is, in modern computers, it's a 64-bit number. So it's a very, very big number, where we then allocate a certain number of bits for the pages, the number of pages, and a certain number of bits for the size of such a page, or the number of memory addresses per page. And we went through an example in the class where we said a hypothetical 16-bit logical address. If we want to, for instance, have, let's say, 1024 addresses in this logical address, how many bits do we need? Well, that's very simple. It's 10 of them. Remember, we went through the whole 2 to the power of whatever, and we actually calculated that to determine how much space we need. If this is a little bit difficult for you to understand, dumb down the problem to just 8 bits. So just think, okay, if we think about 8 bits, and we say that we've got 6 bits in our 8 bits available for the page offset, those 6 bits represent effectively unique addresses. So what is the total number of unique addresses that we can have in 6 bits? Well, you then calculate that and you will get to a number. The same holds true for, that means that we've got 2 bits left for the pages, and that means we can potentially have 4 unique pages in that. If you figure out 0, 0, 0, 1, 1, 0, and 1, 1. Those are the 4 pages. And just extrapolate that now to 16 bits and you will be able to get into such a solution. And I demonstrated how we do this by I showed you a little table that I only used myself. I've got 1, 2, 4, 8, 16, 32, 64, and so forth. And I just start numbering from the second iteration. So instead of from 1, 2, at the 2 I have I've got 1 bit, sorry, 2 bit, yeah, 1 bit, then I can represent 2 things. I've got 2 bits, then I can represent 4 things. I've got 3 bits, I can represent 8 things, and so forth. And that's so just a quick little table like that to help you to determine how many bits is necessary or needed, or quickly how to solve this type of problem. Okay. Then we've demonstrated how to translate between logical and physical addresses. And really, it's effectively this principle. So just remember that the page table it doesn't have to go from top to bottom. We can also represent the page table from left to right, just so that we can get a bit more space in our question paper. But effectively, the idea is, if not asked, you will assume that the 2 most left bits is the page frame, or the page number that we're looking for, and then the other 6 bits, the 6 least significant bits, are the offset. So in the typical example here, 246, if you translate that into binary, it's this binary number. Always make sure that you end up with 8 bits. If you don't end up with 8 bits, then you pad the front, the leftmost, with a bunch of zeros so you can get to 8 bits. Once you get that into 8 bits, you take the 2 most significant bits. In this case, it's 1, 1. You translate that back into decimal, which is the 3. You then do the lookup at index number 3, and you find the corresponding page frame. This page frame 0, 1 replaces that original page number, and then you translate that back into decimal. That's how. There's a whole video that describes this as well, with the link where you can follow this analysis. Any questions on this?
No.
Good. Let me see if there's anything else. As I already mentioned this when we started our lecture, is one of the problems that we have with implementing a page table is this principle of how fast we want the page table to be. Now, to help us solve this problem on how fast we want a page table lookup to be, is to implement a translation look-aside buffer. The translation look-aside buffer basically has a number of features associated with it. For instance, it is typically small, from around 64 to about 1024 entries. It acts as a cache for your different page table entries that you're going to have. We need, another thing is this TLB uses what they call associative memory, so that you can do parallel lookups. That's another thing. What else was there? I think that was about it. So just make sure that you understand TLBs, what is implemented, and basically what it describes and what it will define inside the TLBs. Obviously, there's extra things in the translation loop side buffer, such as your page numbers and the frame numbers will be in there, so that we can do a lookup and define it. And then whenever we do a context switch, the TLBs basically gets flashed and a new TLB entries gets built when you do lookups. It's kind of like the cache as well. That is it for the revision. For the theory. Okay, so what else? Then obviously that was question 4, that was 18 marks. Then we've got 2 more questions that you can expect, question 5 and question 6. Question 5 is the theoretical part of your practical lecture. Now, in the theoretical part, if you look at historical exams and so forth, it was all about IEEE, floating point numbers and how that is represented. You haven't covered that yet in your practice, so you don't have to expect a question like that. But you must know how to translate a 2's complement number into binary. Right? That's part of one of your first lectures that you've had. 2's complement is typically a negative number, and we can take a negative number and you can translate that negative number into binary, and one of the mechanisms to do that is using 2's complement. You need to know how to do that and be able to translate. Also, you need to understand how the stack diagrams work for a specific type of function. Right? Making sure that you understand the number of parameters in the function and the type of parameters. Because if you think about it, a parameter can either be an integer value or it can be a pointer, meaning an address of something. We typically have an address of something when we refer to an array. So if we send pointer to an array as a parameter, don't tell us that that is the array. That is incorrect. It is the address of the array. It is the value of the number of items. Make sure that you understand that that is how it should be reflected in your stack diagram. Those things and your parameters are always, the first one is always at EVP plus. Make sure that you understand when you look at a typical C++ function or any kind of function, and you read from left to right, the first parameter is always at plus 8. The second parameter is always at typically plus 12, and then it's plus 16 and plus whatever. Okay. So make sure that you have that order correct as well. So what is an EVP plus 4 then? It's the return address of the calling function. Then you've got your whole EVP, and then at EVP minus, you may have a local variable, maybe not, but you will definitely have a number of registers, and you will have your flags that gets stored in there. Now, when you think about the registers, make sure that you consider whether EAX should be one of those registers. EAX is only gets pushed onto the stack if you have a void function. If you have a function that returns something, then the EAX should not be part of your stack. Remember that. And then the last, so that is 10 marks for all of that theory part. And then question 6 is your assembly language. And again, there's easy marks. Don't think that you can't do it, guys. There's easy marks that you will always get. And think about now, you will be given a function to represent. Now, there's always a certain pattern that you will always find in any function. giving at least that pattern will give you some marks. Very important things that we look at is again the role of EAX register and the order in which you push. When you create your stack frame and you're destroying your stack frame, make sure that you do know when you push things in a certain order in the start, make sure that you do the inverse at the bottom. Make sure that you understand that when we have a function again that returns something, meaning it's not a void or something like that, then EAX should not be part of the pushing at the top. And then the last thing that you will always have is your rent. Okay? Rent. That's the keyword, and then a value after that. Now the value is not some magic thing, it is the number of parameters. If you've got 2 parameters, then the value is always an 8. If you've got 1 parameter, then this value is always a 4. If your function takes no parameters, then it's red on its own, nothing after that. Right, so that's the basic principle, and then obviously the stuff in there is just a mean. That's when you can basically get, okay, do we really kind of understand what you're doing. But you have to also know how to access array items. How do you access specific items inside an array? That's the type of thing. And then obviously doing some multiplication, division, and that with it. So loop structures is maybe do something with an array item, and that's question. Don't discount the assembly stuff, right? It's like 3 marks. You do something. Yes. So question 5 was, as I said, was 10 marks, and question 6 was 15 marks. 1 5. So exactly like we had. There's another hand. Sorry guys, come here. Sorry. Okay, will I ask recursion? I don't know. Recursion is just a function that calls, again, that will have call in it. It's really not, there's nothing to it. There's a question here. Sorry guys.